Hey guys, for the next few minutes we'll walk through the split Hopkinson bar analysis tool. This is version 2 and you can find this file at the MATLAB file exchange description linked below. And you can get just a raw M file with the fig file and run it directly in MATLAB, or if you do not have MATLAB you can download the runtime engine, and I will also post in the description an executable so you can still access this program to analyze any of your voltages from your split Hopkinson bar tests. So let's jump right into it. First, with how do you get your information in? So importing data. Try to anticipate as many different ways you could import data in. So again, go to File, Load, Gauge Voltages. On your incident and your transmitted bar could be grouped or not grouped. So if they're grouped, you could have them grouped in an Excel file together, like two columns right beside each other. Or they could just be somewhere random in an Excel file with a bunch of header information in there. So if that's the case, where they're not strictly just two columns only, then you need to go to the interactive importing option for group data. If, however, your Excel file simply has two columns of information and nothing else in the Excel file, then you can use the automatic feature and then just pick your file. I'll show the interactive version. So it'll give you a prompt to explain what's happening. So let's go find this Excel file. And again, this uses the function within MATLAB XLSRead. And it's kind of a slower function, I suppose, because it's calling Excel server applications and it has to boot it up, so it's not quite as quick if you're as it would be if you're just importing a data file or something. Okay, take note of what happened here. This box popped up telling you to select your data region. So Excel booted up, and so here we go. There's a bunch of header information. Here's the two channels I'm interested in. That's for the incident bar. This is for the transmitted bar. Don't click OK, because when you hit OK, it will just take whatever you've highlighted. So I want these two columns all the way to the end. OK, so it's going to take those two columns of data that I've highlighted, and now they live right here. And that's sample 9, that's this file. So it just pulls whatever that file's name is. If you want to have more information in there, so you say you had multiple strain gauge, multiple tests, you can do the same thing again. Let's go interactive. Do the exact same thing again, and it'll just put a _1 or _2 wherever you're at. So you have unique names every time. Again, don't hit OK. If you do hit OK, let's show you what happens. Whoops. Data wasn't imported. It realized that you forgot. So no harm, no foul. Just go do it again. Yeah, and this is the slowest part of it all. If you're going to pull stuff in from Excel, so I would recommend, if you can help it, try to save your voltage files as some sort of data file or CSV file. Excel is a bit slower for importing information in. And that's strictly, again, just due to the time costs of of the XLSRead function. Okay, here we go. It's booting up again. Alright, it's loading it in. Alright, so now we have two files. That's just the second one, and to put an _1 for a different name. So we'll just call this one sample 2 or something, and we'll call this one sample 1. Okay, so now we have those two. So a couple different options. So say our data was grouped already in a data file. and for this case you have whatever type extension you have on there. We'll choose CSV. This file already has strictly, again, just 2 columns alone, nothing more. And we've got it in there, so we'll call this stainless 1. Alright, now finally, the same type of thing with ungrouped. You can go interactive and go dig into an Excel file and pull out 1 column of information, and you'll do that twice because it's assuming it's ungrouped. So you'll go in, pull it out once, and then it'll boot up Excel again for you, and you'll pull out a second column. So we'll do an ungrouped data file. And it tells you what you're looking for there. Okay, so for this case, this was native to a particular test we were running. It's saved as a .001. That's an incident bar file. So again, that's much faster than importing from Excel. So if you can help it, try to save them as data files. There we go. So there we go. You can, there's these boxes here if you want to make notes about the material, your source, any other type of information, you can. Alright, so let's now move, I guess I should say one more thing. We will go ahead and write a restart file from everything we've done from this point. We've got 4 different data sets loaded in. Let's go ahead and write a restart file. So write sample data, a restart file. You can name it whatever you want. The default's today's date and a restart. So let's save it in there. And there it is. It's there. And if you're curious, you can see it here as well in MATLAB, and it's a structure that it's saving. And then what I can do is I can re-import everything I've done. So I have 4 files now. I could import that restart file again, and it'll pull those 4 back in. So I'm going to have 8, where a lot of them are identical. That's okay. I'll just go ahead and do it just to show how it works. Okay, there it is. And now I've got 8. So those are all duplicates, so they have more. Oh, I guess I'll show, you can go ahead and delete a file. So I want to delete everything I just brought in. You can right click on the data set and delete it. And let's delete that. There are these other options here about plotting, isolating and unisolating plots. I'll show that in a second once we get to the final step of visualizing our data. So now it's time to look at our voltages and do something with them. We can hop ahead and crop our data first. So this is our signal. So nothing much happens, the impact happens, then it decays. So the information I'm interested in is somewhere, before, and then, I don't care about this much, but somewhere around in here. And let's refine it. So you get an option to do a 2-step cropping process if you want, or if you're okay with that, you can say fine. But let's go ahead and refine it. Okay, telling me to click 2 points. So click on the left side of where you want to start, and then the right side of where you want it to end. There we go. That's fine. And it'll put a check mark once you've done that. You can't uncheck or recheck any of this. It just, once you finish a step, it will populate that box with a check. So let's go ahead and find what this step is finding the null. So it's it's close to 0, but you again bracket your data, click on the left and right of it. It doesn't matter if you click to the left first or the right first, but I've clicked on either side, and it averages any of the signal within what I've clicked, and it gives you a pop-up box to show what that value is. It'll show you your raw data that you've bracketed, and then the null signal. So it raised it from -2 to 10 to -3 to closer to a 0 signal. Okay, so now let's check that off. So you do the same thing for your transmitted signal. Click on the left and right of where you think your 0 signal is. And then if you need to, you can invert your signals. So this program, it matters whether or not you're in tension or compression, because you're going to be reporting true stresses and true strains if you want to. You can still just look at engineering stresses and strains. So, but where that comes into play is you calculate true stresses and strains, not differently, but it really matters whether it's positive or negative, because you're going to be taking natural logs of things, and so inverting your signal is important. So we'll assume, okay, I got an error, so I wanted to go ahead and do some wave clipping where I actually try to isolate the signals, but it's giving me an error because I haven't created any bars yet for this sample. So I don't have any here. I need to create a new one. So it's giving you instructions to say you need to give your bar tag, so let's say it's a steel bar, gauge factor. For our setup here currently it's this. So this is a strain to voltage. Your strain gauge should give you that. Or you may have to work it out depending on how you've laid out your strain gauges. Your sampling frequency, again, note the units here, we're in megahertz, so 2 megahertz. So you have your diameter of your bars, and then there's 3 different options here for modulus, density, wave speed. You only need to fill out 2 of them because the assumption used in the analysis is a one-dimensional wave propagation, and so if you these 3 values are could be calculated from the other, so that each value is a function of the other 2. So that's to say, whichever one you know for your particular setup. So for instance, I know mine, the density is 8,000 kilograms per meter squared, and the wave speed, I think somewhere around 4,750,000 meters per second. Okay, so now I can then apply that bar I just made, and if I need to go edit it, I can here. And it's again telling you, here's that relationship where your wave speed squared equals the modulus divided by the density. So I brought that back in there. Okay, let's just keep it as it is. Now let's go to wave clipping. Alright, so this is a new feature compared to the previous version, where this is generally the most time-consuming of your data analysis, where you're trying to isolate the incident wave, which is, you can see down the bottom left, the reflected wave, which is in the center at the bottom, and then your transmitted wave. Before I had an algorithm that attempted to get that right when you imported your signal, but I found a lot of folks that were using this said that was causing lots of issues for them, and it was. And so what I've decided, instead, I still have included an auto-align feature, which uses the signal processing toolbox in MATLAB. So if you don't have that toolbox, this button won't work. It'll it'll just pop up a box and said, we've checked and you don't have this toolbox installed. But the nice thing then is, so here's what happens. If you say auto-align, you'll get a pop-up box where it's running a genetic algorithm to try to find how to best align the waves. So the signal processing toolbox still didn't get where the incident wave began very well. It needs to scoot over a little bit. Oh, and so you have, again, 3 sliders, incident, reflected, and transmitted, that shows these correlate to the beginning point of each wave. And we'll talk again, the top 6 plots, we'll get to there in a second. So you can manually go click through to find a good position to begin, and then at the very right side you have pulse width, which is the length of the pulse, and you can increase or decrease that. So if you don't have the system processing toolbox, or the signal processor toolbox, what you can do is just go find the incident wave and then align everything to that. So let's say this is our wave that we wanted to say, here's our incident wave. So the align to incident feature, if you have, this is what you click now, and there's two things will happen. You'll see one or two things happen if you click this button. If you have the optimization toolbox installed, then what it will do is it'll run through a genetic algorithm to find the best fit for the reflected wave and transmitted wave. If you don't have that installed, it's fine. What it'll do is it'll run a nested loop over all the possible reflected wave and transmitted wave and find where the error in the force balance is the least. So let me go ahead and align to increment incident, and so it's running the genetic algorithm. And what it's trying to minimize is right here, this difference force balance, which all it is the strain. If you were to take the first point of the incident wave, the first point here of the reflected wave, and the first point of the transmitted wave, and then you took the incident and subtracted off the reflected and then transmitted, and then do that for every point in this array, you want to minimize where you want that to be minimal. So that means that your specimen is seeing equilibrium. So that's what's going on. I won't do any further explanation. Shoot me an email, respond. You can send a question in the MATLAB file exchange if you have more questions, or just look in the MATLAB file and you can see how that works. So again, in the second row, first column, you can see all these waves lined up. Oh, one other thing I've neglected to mention. This window is resizable. It can't go smaller than its original size, so if you try to, it'll kick back, but you can do a full screen. I probably should have been doing this in the other parts of the video. So you have force balance for the incident bar, the transmitted bar, this force difference, and force displacement, displacement time, velocity time, and this is a one-wave versus three-wave analysis. You can go read the paper or just Google what the difference is between a one or three-wave analysis. Okay, so I'll assume I like that. Let's go ahead and accept it. Alright, so it's going to say, based on the wave pulse that we're looking at here, it's assuming that the sample was in tension. And how it's guessing that is, this first wave kicks up. The incident wave is positive, so it thinks that's a positive strain. It's a tensile strain, so it thinks you're in tension. So if that's the case, hit confirm. If it's not, hit cancel, and then go ahead and flip these over. Invert both the signals now. So now your incident wave begins negative, and the reflection of that would be positive. That makes sense. And your transmitted wave also needs to be negative. So if that's the case, if you want to say accept, it'll ask you, all right, it's reading that it's a compression. So you confirm or you can cancel. Let's put them both in tension just for the time being. So we flipped everything back over, accept, confirm. All right, let's run one more sample through here. Let's do stainless. And again, you could try to do rough crop. It's going to argue with you. Oh, it'll like that. But then when you get to wave clipping, it's going to argue with you. So let's crop. That looks good. So we'll accept it. We won't do the two-step crop method. Let's null the wave. Alright, wave clipping. Oh, it's arguing because I haven't said what bar was used. So let's say that steel bar was used in that test as well. Alright. It looks like this was just random luck. There's no reason why it happened to. It looks like it got the incident wave, but I think I have the program set so it does like at the 20th. If you were to look at the length of the wave, go to 20% of the from the beginning point or something. So there's no reason why it happened to catch that correctly. It just got lucky. So let's assume that it's not as lucky. And okay, let's go ahead and auto align this. Usually this unload, that's not real, and you don't really want that. You're not going to report that usually. Certain cases where you might, but here you're going to want to remove this tail. Alright, now let's go. I haven't aligned the reflected or the transmitted wave yet to this. So let's go ahead and align to the incident wave. If you feel like, well, it did find the best fit, the minimum for this force balance, but you can see from the reflected wave that it doesn't quite get back to 0. So if you want to override that, no problem. Just go ahead and go back a little bit more. This number will increase because this is the sum of all of the area underneath this force balance. So it's going to increase. Not increase the whole SCOs, that's 1100, whereas if aligned to the incident, what was it? I think it was around 900 or 800 or something. Yeah, right around 900. So again, let's go ahead and accept that. Confirm. Alright, dispersion, if you want to include it, you can. It's there, similar to last. You can put in a predefined Poisson's ratio between 0.2 and 0.35. Look at, if you're curious, some of the theory behind this, you can click the publication site button, and it should pull up in whatever browser you use. It'll pull up that article. So here we go. And this is the old version right there. And once this video is complete, it'll be in the video tutorial button. Documentation will take you to our cyber infrastructure here at Mississippi State. Alright, so now it's loading that up. Whoops. Alright, there it is. So there's the code for the split Hopkinson bar analysis. Alright, so now the next step would be to, let's look at stress strain curves. That's the end goal for these. So if you want, that would be in the plot display. You bring down, you have a couple different options on how you want to, how much information you actually want to look at. Say we just want to look at stress versus strain. What it's telling me here is all the data set were removed from the plots because none of them have been completely prepped to be displayed. Now we did a lot for these first two. This sample 1, we can see here we have these check marks done. Sample 2, we haven't done anything for this yet. Stainless 1, oh, there. This one's been pretty much done. This SS, nothing's been done. However, what has not been done is a geometry has not been applied. So let's say our length was 1 millimeter and our diameter is 1 millimeter. So now if I want to plot and display, there it is. The other one was ignored, so we did a lot of work on this one, but we still haven't given it a length and a diameter yet. So now it will tell us certain things were not done to sample 2 and SS, but the other two are good to go. So there they are. Now you have options here to what do you want to look at to determine, are you happy with your tests, or you're ready to export this and write a paper about it, or look at the data. What do you want to do with it? So you have as many options as you want to poke through your data sets to whatever you'd be interested in looking at. So we have first default with the true stress and strain, engineering stress and strain, force displacement, true strain rate versus the strain, the engineering strain rate versus the strain, and then the transmitted rate versus the time. If you want to change any of it, it's fully customizable and it will remember what you've changed per each session. So say I want to go over here to this plot and I don't want to look at the transmitted wave strain, I want to look at the reflected. So this is numbered 1, 2, 3, 4, 5, 6. So from the top left to the bottom right. So It updates. My x-axis is time, my y-axis is transmitted strain wave. So I want to look at the, I think that's the reflected. Okay, so there's my reflected, or if I want to look at the incident. I don't want time, I want it to go over the engineering strain. Pick whatever you want. You can edit any of those to your heart's desire. Right, so say you can just look at one, or if you want to look at a 2 by 1. Whatever you want to do. You can have 5 different options on how you view your data. Okay, so this is pretty much it now. It's time to write your information, what you have currently stored in the system, out. So you can, again, you can send it to a MATLAB. Oh no, let's before we write, you also have the option. So say you had 20 data sets in here and you didn't want to look at them all at the same time. You'd completed all the analysis portion, but you wanted to just look at one at a time or something. What you can do is you can right click, or pull up a data set. So say I want to look strictly at sample 1 and I don't want to look at anything else. You can right click on it and you can isolate the plot, and now if I go back and replot, it will just be sample 1. And you can unisolate any plot, or you can and then you also can, if you had 20 sets and you only want to look at half of them, where you can disable the plots that you want or enable them so you can view things inside here. Alright, finally let's go move into the write portion. You can write to an Excel file. You can do a single file, or you can do all of them. If you choose single, what it's going to do, it's going to look at your data set that you have currently up at the time in your data set pop-up menu. If you write all of them, so let's go ahead and start with MATLAB. If you want to write all of them, it's going to give you the same pop-up as when you were trying to visualize your data. It's going to say 2 of your data sets, you haven't finished working on them yet, so it's not going to export those. You can do your restart files with them, but you can't actually send out meaningful data yet. So okay, that's fine. And you'll get a pop-up with the default is today's date and then an export. You can write whatever you want in here. We'll just leave that as it is. Of names. Oh, a bug. I'll get that fixed. It's just I forgot to say if you've got. So this one we had 4, but it's only exporting 2, so it just needs to catch that. No problem. So let's go ahead. So to bypass that error, so I can go ahead and get this video posted, let's delete that plot, and then let's delete that data set, and let's delete this data set. Alright, now it should write without arguing. Okay, there we go. And what that file looks like, just so it'll be a structured array. MATLAB, let's clear this off. Okay, where it's got those 2 data sets, and you've got all of these different arrays that you can work with. It's the same things that we were plotting earlier, but it's here so you can do whatever you want to with them. Also, if you want to send it out to Excel, what you can do is, let's send them all out. All right. You can do it. Again, that's a bit more time consuming. It's using the SLS write function. It takes a bit more time as opposed to writing a mat file for MATLAB. Okay, so what we see here, this is what was written. These are the 2 different data sets that we had completed. If you had more information, like notes and material types and those type of things, they would fill in here, but we left those blank, so it just has the file name, the tag that we gave it, and then the export date, which is there. And we have all of this data, which was calculated. You can do whatever you want to with it. Future versions, I'd like to, one thing has changed is play with the units, so that within the GUI you can edit your the units that you want to use, metric or imperial or even swapping between pascals, megapascals, millimeters, meters, that type of thing. Alright, let's don't save that. I think that could conclude. Oh, one final thing is you also have the option if you just want to save, say you had a particular setup with your bars, and you didn't want to always retype in the bar information. What you can do is you can write a bar restart file here, and you can always import, load in just a bar and not data sets. So pick a restart bar and it'll send it into here for you. Alright, with that I will stop this video. Again, feel free, look in the description below. There's going to be some helpful links, and don't hesitate to reach out to me. My contact information should be, you can reach out through the MATLAB website or through the university website in the link below. One last thing I forgot to mention is there's an option to calculate your strain rates. Again, this is, with dynamic testing, it's really hard to say. You don't have a constant strain rate. It's not like you're running just a quasi-static test where you really can control your strain rate. This is dynamic testing. So with that in mind, there's this button here called Calculate by the strain rate box. If you click it, it'll bring your 8 different plots up. You have the top row is strain rate, the bottom row is strain versus time. In each corner you'll see something that says E1, E3, T1, T3. That's engineering strain rate, one wave analysis, engineering strain rate, 3-wave analysis, and then this is true strain 1 wave, true strain 3 waves. Same thing here is on the bottom row instead of strain rate, but you're just looking at there. You see dotted lines on all of your plots as well. What those correspond to is for the top ones, just averaging every point in this array, and then whatever that average is, I just drew a line across it at that value. At the bottom, for these guys, I ran a least squares polynomial, just a linear fit to that curve, and the slope is the slope value in this top corner is the slope value of that dotted line or dashed line. So you can look at all those values and then determine what you think is best to report for your strain rate. Again, there's not an exact answer there, so it's up to your engineering judgment.